Let's try and work out this magnetic field numerically. I've written a Python program here to do it, based on the various previous programs we've written. And let me talk you through what's going on here. So we set up constants, mu0 over 4 pi, the current and the length. We set up a measurement position. So I'm going to assume we have a current of 2 amps and a rod of wire of length 10 centimeters, and we're measuring the electric field 5 centimeters from it. Then we'll pick a step. We're going to step up and down the rod in steps of, that's a millimeter. And we're going to add up the magnetic field. We know the only magnetic field component that matters is the Z one, so this is just the Z component. We don't need to worry about the X and Y components. Now we set up a loop. We'll start at the bottom of the rod, y equals minus 0.5 times L, and we'll keep going while y is less than the top of the loop. So 0.5 times L, and I've added, as we've seen before, a very small constant to let it actually get up to 0.5 L rather than stopping slightly below it because of rounding errors. Then we calculate the electric field due to this component with the equation we saw in the last video, the constant current times x times dy over x squared plus y squared to the 1.5 power. So that's worked out the little bit of magnetic field due to this particular delta y, and we add it to the sum. So the sum b sum starts off as 0, and then every time we go through the loop, dB is added to it. So by the time we finish, it'll tell you the total magnetic field, which we print out over here. So very straightforward. And if you run it, it gives us a field of 5.68 by 10 to the minus 6 Tesla. If we make the time step smaller, let's see if that changes. So I made it 10 times smaller. Now if you run it, it's 5.66 as opposed to 5.68, so it's a very small change. If you make it even smaller still, 5.657. So it looks like we're accurate to at least 3 significant figures here.